Hello students, today we are going to deal with a new chapter on vibration, mechanical vibration, that is multi-degree freedom vibration system. We have already discussed 2-degree freedom vibration system in our earlier classes. This multi-degree freedom vibration system is nothing but an extension of 2-degree freedom system. So in this lecture, what I'm going to cover is we'll discuss about the analysis of n degree of freedom system, and subsequently we'll try to derive the equation of motion and would propose the solution for this n degree of freedom system. The purpose to solve any n degree of freedom vibration system is to calculate the natural frequency. As you know that if it is n degree of freedom system, there will be n natural frequencies existing for the system. At the same time, we are also interested in calculating the mode shapes of these displacing masses. As I have already told you that as the number of degree of freedom increases, the computational complexity of frequencies of the combined system increases. And in this first method, we are going to discuss the analysis part of multi-degree freedom system by simply extending the method which we have adapted for analyzing 2-degree of freedom system. So let us take one n-degree freedom system which is undamped, without damping, and there is no external excitation force acting on this. So there are n spring mass systems are attached with each other in such a way that individual displacement of individual mass would be independent of the displacement of other masses. It means that the coordinate of displacement of each mass, x1, x2, x3, so on and so forth up to xn, are independent. Therefore, the system is n-degree freedom system. Now, this n-degree freedom system has got n masses, which are shown in the diagram. M1, which displaces by an amount x1, M2, which displaces by an amount x2. Similarly, Mn mass, which displaces by an amount xn. Now, in order to write down the equation of motion for this complete system, what do we need to do is that we have to individually, first of all, draw the free body diagram of each mass. So, in order to do that, what I will do is that I'll take this mass M1. Since this mass is connected with two springs which are having stiffness, assume that K1 and K2. So if I want to draw the free body diagram of this mass, which displaces by an amount x2, and the subsequent mass which is attached with this mass displaces by an amount x2, then the free body diagram of the first mass can be drawn where it is subjected under a spring force, because since this mass is moving downwards, this spring is going to exert a force on mass m1 upward, that is equal to stiffness k1 into the displacement, that is x1. So this force is exerted by the spring on the mass, that is k1 into x1. Similarly, let us take an example of this spring which is connected to the mass m1. This spring is subjected a compression of x1, since this mass is moving downward by an amount x1, that compresses this spring by amount x1, whereas the next mass which is attached to the other end of the spring moves x2 amount downwards, so that extends the spring by an amount x2. So the net expansion of this spring, assuming that x2 is greater than x1, the net expansion of this spring is going to be x2 minus x1. If you assume that x1 is greater than x2, then the net compression of this spring is going to be x1 minus x2. So since this spring is compressing, so this is going to exert a force upward on this mass. And how much is that force exerted by this spring on this mass? That would be equal to spring constant K2 multiplied by net compression. Net compression of this spring is x1 minus x2. So the force exerted by this spring on this mass upward would be K2 into x1 minus x2. Since this mass is moving with an acceleration x1 double dot, so there would be an acceleration force acting downwards in the direction of movement of this mass, that is m1 x1 double dot. Now from the Newton's law, we know that acceleration force is equal to the net force applied on the mass. So the acceleration force is m1 x1 double dot is equal to net force applied, since the direction of this k1 x1 is upward, which is opposite to the acceleration force. So we'll have to write here negative sign. So minus k1 x1, and this force is also upward, so it has to also be written with negative sign, that is minus k2 into x1 minus x2. Simplifying this equation in such a way that taking x1 common would give rise to this equation of motion for the mass m1, that is m1 x1 double dot plus k1 plus k2 into x1 minus k2 x2 is equal to 0. Similarly, we can write the equation of motion for mass m2. So there is a mass. If you observe from the previous slide that this mass is connected with a spring constant of k2 and with this spring, which is spring constant k3. The net compression of this spring, which we have already dealt here in this mass, is x1 minus x2. So if this spring is compressed, this is going to exert a force in downward direction on the mass m2, that is k2 into x1 minus x2. Similarly, this spring, assuming that x2 is more than x3, so again would compress the spring, because x2 is downward, x3 is downward. So the net would be a compression of this spring. So the force exerted by the spring on this mass would be upward, that is equal to K3 multiplied by net compression. Net compression is x2 minus x3. So going to the free body diagram of this mass M2, These are the two forces which have been calculated. Additionally, there is a force since this mass is moving downward. So acceleration force is acting downward. That is m2 into x2 double dot. Now this equation of motion, again by using Newton's law, can be written as m2 x2 double dot acceleration force is equal to the net force acting onto this. That is, since this force is acting in the same direction as acceleration force, so it comes with positive sign, k2 into x1 minus x2. Whereas this force is acting in negative direction, so it comes with negative sign, minus k3 x2 minus x3. Now simplifying this equation again in such a way that we take x2 common. Now I write this equation in such a way that it forms, first comes as the x1, coefficient of x1, then comes the coefficient of x2, and I simplify this equation in this format. This is simple, you can mathematically calculate and write down this equation in this form. So here one thing is important to see is that this equation that is being written for second mass connected with the spring K2 and K3 has an equation minus K2, that is spring coefficient of upper spring, multiplied by x1, that is the displacement of the upper mass m1, then m2 into x2 double dot plus k2 plus k3, the sum of the spring coefficients of the two springs, minus k3 into x3, that is the lower mass displacement and spring coefficient. So in that way, we can write the equation of motion for the third spring as, from here we have done it by writing minus sign spring coefficient of the previous spring, that is K2, into displacement of previous mass x1. So for mass 3 we can write here, similarly we can write for mass 3, that is minus K3, the spring coefficient of the upper spring, multiplied by the displacement of the upper mass, plus m3 into x3 double dot plus k3 plus k4 into x3 minus k4 x4. So this equation can be easily derived in the similar way as we have derived for mass 2. Similarly, in this way we can write all the equations for all the masses in the system. Now here, whilst writing the equation of motion for nth mass, you would find that this mass is connected with only one spring, that is upward. Okay. So drawing the free body diagram for this spring, that is Kn, you would find that this spring gets compressed by xn minus 1 minus xn amount. So this is going to exert a force downward on this mass mn, and there would be an additional acceleration force on this mass that is downward. So analyzing or drawing free body diagram of nth mass, we can show the spring force coming on downward direction, and there is an acceleration force downward. So writing equation for this and solving this would give you the equation of motion for the nth spring. So in this way, we have calculated the equation of motion for all individual masses. Now, writing these equations, starting from mass 1, for mass 2, and mass 3 and up to n, would give you the equation of mass, equation of motion for the individual masses in n degree of freedom system. Now, solution to these differential equations, equation of motions, can be proposed as we have done in case of 2 degree of freedom system. x1 is equal to capital X1 sine omega t, x2 is equal to capital X2 sine omega t. Similarly, xn is equal to capital Xn sine omega t. Now, putting this value of x1 in equation number 1, equation of motion for mass 1, you need to put the value of x1 double dot. This you will get by double differentiating this solution. That would give you minus omega square x1 sine omega t. So putting these values out there, x1 double dot, x1 and x2 value, sine omega t would be common, so it would cancel out. And the equation comes out to be in terms of coefficient of x1 and x2. Similarly, putting all other values in equation of motion of mass 2, mass 3, and mass n, you would get the equation of motion for all these individual masses in this way. Now, this solution actually you can write in a matrix form where you know that each equation has coefficient of x1, x2, the coefficient of x3 in this equation is 0, x4 is 0. So write those coefficients 0 in the matrix form. Similarly, in the second row, we can write for second mass, the coefficient of x1 as minus k2, coefficient of x2 as this value, coefficient of x3 as this value, and similarly x4 coefficient is 0. So we can write this equation in the form of a matrix where first row represents the equation of motion for mass 1, where this value represents the coefficient of x1, and this value is written in the second place, which represents the coefficient of x2. Since the coefficient of x3 is 0, so it is 0, and up to n, all other values are 0. Similarly, for second mass, the coefficient of x1 is minus k2, so minus k2 is written here. Coefficient of x2 is this, so it is written here. Similarly, all other values are 0. Similarly, for mass 3, the coefficient of x1 is 0, so we'll have to write coefficient of x1 0. Coefficient of x2 is minus k3. So we can write this in matrix form is equal to 0. Now, solving this equation would give you n degree freedom, n degree would give you an equation of omega power n. And through that, omega square power n, and through that, you can actually calculate the corresponding n natural frequencies. But so bigger is going to be this matrix size, more complex is solution, getting solution of this out of this matrix. What you need to do is that you can use a computer algorithm to actually solve big matrices. But after certain size, when the computation size becomes bigger, even the computer takes much time to solve such problems. So this is one method of calculating n natural frequencies of n degree of freedom system. In my next class, what I am going to discuss is we are going to discuss a new method for solving such problem, that is n degree of freedom system, by using matrix method. And we would explain matrix method by taking a suitable example. So You would learn in that lecture how to solve one method we have already dealt by analyzing n degree of freedom system and calculating n natural frequencies. But this matrix method may be more simpler method in which we can use eigenvalues and eigenvectors to calculate n natural frequencies of n degree of freedom system. So bye for now. We'll come up with the next lecture on this, and we'll discuss about a multi-degree of freedom system more in detail. Thank you.